Hey students, welcome to Sustainable Energy. I'm Rudi Schlaf, a professor in the Electrical Engineering department at USF. This is part 1 of the Unconventional Fuels segment. In part 1 we will discuss unconventional gas, we will discuss the reserves of unconventional gas, horizontal drilling and fracking technology, and we will also look a little bit into the environmental issues of these technologies.
So, what are unconventional fuels? Here we have a figure from the Canadian Association of Petroleum Producers, their resource triangle. They say that conventional resources are those small volumes that are easy to develop. So this is the tip of this pyramid. And then the unconventional resources are large volumes that are difficult to develop. And so here we have tight gas, coal bed methane, shale gas, and gas hydrates. So this is obviously just for gas. You may have heard there are also unconventional liquid fuel sources. The most prominent ones are oil and tar sands that are mainly found in Canada. In general, we can say that unconventional fuel sources are more expensive to extract and that they also have a lower energy return on investment than conventional sources. That means that unconventional fuels can never be produced at the same low price point as conventional fuels. The most valuable unconventional source is probably gas because of its lower carbon content per energy. If we replace coal with gas on the way to sustainable energies, we can consider the gas as a transitional fuel source. Okay, let's look into unconventional natural gas. Here's a graphic from the Energy Information Administration summarizing natural gas resources. And when it comes to conventional resources, we have typically large volumes that are underground, and one can simply drill into them and then tap the gas and let it escape. There are two principal kinds. One is non-associated gas, so we have only gas, and the other conventional resource for gas is conventional associated gas, which is associated with oil resources. So conventional oil often has a volume of gas above it. In fact, in many cases, this gas is simply flared off because it is considered a nuisance while extracting the oil because there is no infrastructure such as pipelines to bring this gas to customers from many oil fields. Now, when it comes to unconventional gas resources, such gas is trapped in geological formations in small volumes. Think of gas bubbles inside rock. And the method to extract that needs a more advanced technology. What has been developed over the last 10-20 years is hydraulic fracturing, also called fracking, and directional horizontal drilling. So this allows to do something like this. You can drill into a shale formation, for example, and then horizontally penetrate this shale formation and thereby access a large volume of it, and then by pressing in a fracking fluid, the geological formation is fractured, and that releases the gas from those small volumes in the rock, and then the gas escapes through the wellhead and can be extracted. It is interesting to consider the gas production forecast. Here we have a graph from the British Petroleum 2035 Energy Outlook. Every few years they publish a new energy outlook, and the current one goes to 2035. So here they show the gas production from 1970 to 2035. So they forecast that in non-OECD countries, so non-OECD, these are mainly developing nations, that in such countries the main increase of the gas production comes from conventional gas sources. So that's what they call other here. If you look at the production forecast from shale, so from unconventional gas resources, there's only this little sliver. Now, in OECD countries, or in other words, in industrialized nations, we already went through the conventional gas production peak. So you see it here. It was somewhere around 2000. And therefore, most of the increase is from unconventional sources. So you may wonder, why aren't the industrialized nations simply buying the conventional gas from other countries? Well, the reason for that is that gas is more difficult to transport than oil because you have to essentially liquefy it if you want to ship it across an ocean. And so gas is best sold close to where it is produced, or at least where one can build a pipeline. So having said this, if you think of the industrialized nations, most of that increase in unconventional production is actually in North America. In the case of Europe, because it is on the same landmass like Russia, pipelines could be built between Russia and Europe, and so a lot of the European gas comes still from conventional sources located in Russia. Even though most of the near-term increase in gas production will come from conventional sources, there's no question that unconventional gas resources will make inroads. Here is a graph from the World Economic Outlook, which is published annually by the International Monetary Fund. On this graph, they compare conventional and unconventional production. And so what you see here, the purple and the orange bars, these are the conventional production, and the green bars are the unconventional production. And you see, while the conventional ones are still increasing, the unconventional ones are also increasing. The green curve with the scale to the right, that shows the part of the unconventional production relative to the total. And so you see that over the years it will go up considerably. But even in 2030, we will have less than 15% of the total output from unconventional resources. If you think of the amount of unconventional resources that are in the ground, it is currently believed that they vastly outrange the conventional resources. But as you saw on the first slide, the unconventional resources are typically more difficult to get to, and there is no question that the conventional resources will be depleted first, and then we will resort to the unconventional gas resources. So where are these unconventional resources located? Here's a map from the Energy Information Administration. And so you see that the United States and Canada, they have one of the larger deposits. It's estimated that there are 862 trillion cubic feet that can be accessed. If you add all the other known resources together, that comes up to another 6,600 trillion cubic feet worldwide. And so these are only the resources that have a solid resource estimate, so fairly good data. Now, all these grayed out countries, there the data is not good, and so they excluded it from this estimation. So if you only consider now the ones that they added up here, the 660 trillion cubic feet plus our 862 in North America, then we can estimate that this would add about 60 years of supplies at the current rate of 110 trillion cubic feet per year worldwide. If we speculate that the grayed out areas have another a similar amount, there's a lot of speculation going on around the internet, but it's most likely that at least Russia has some very significant resources. It's easily possible that there is 100 years of supplies or so in the ground in terms of unconventional resources. Here's a close-up of the US. Our unconventional resources are mostly found along the Appalachians, in Texas, and here in the Rocky Mountains. So now it's time to look into the technology that is used to extract unconventional gas resources. Since the unconventional gas is trapped in rock formations underground, there is no obvious escape path for the gas, and so ways need to be found to crack that rock open to make percolation pathways for the gas so it can escape into the well. There are two key technologies that have led to the ability to extract this gas. One is horizontal drilling, and that enables from one drilling site to penetrate a rock formation far underground in various directions. And the other one is hydraulic fracturing. Once these wells are in place, a liquid is pumped in under high pressure, and through holes in the pipe, the rock is cracked by that high pressure fluid. Once these cracks are there, the methane can escape into the well and then can be extracted at the wellhead. The challenges with this technology are that usually the rock formation is below the drinking water aquifer, and so there are issues with fracking that these cracks reach up to the aquifer, and so gas can directly mix with the water, or that around the well cracks allow gas to enter the water supply. The other issue is during the fracking process, huge amounts of water and chemicals are being used to crack the rock, and so part of that fracking fluid stays underground, and the part that's being recovered that often is stored in ponds and so forth around the drilling sites. There's no question that horizontal drilling reduces the environmental impact because of the entrapment of the gas in the shale rock formations. One needs many wells to go into that rock because the cracks caused by the fracking process, they only reach that far. And so if one wants to get the gas out of the entire volume, one needs many pipes and fracked areas to access the gas. And so with relatively few wellheads, because of the horizontal drilling, we can get at these reservoirs much more efficiently. Here you see a picture of a drill head that's used in horizontal drilling. The idea is that the end section of the drill heads can be tilted, and so we can achieve a certain off angle. You can imagine once you tilt the head like this, it will sort of go around a curve, and thereby you can go from vertical down drilling to a horizontal drilling inside a shale formation. A popular approach to this is to use a hydraulic mud motor. So the fluid that they pump down, the drilling fluid, is called mud, and the pressure in that drilling fluid that can be used in a turbine-like device here to create rotation, and so with this drill head can be turned. The drilling fluid is often also used through jets under high pressure to actually cut little slits into the rock that make it easier for those diamond grinders to grind the rock off. That enhances the drilling speed quite considerably. Once the horizontal drilling process is complete, the hydraulic fracturing starts. In this process, the rock is being cracked with a liquid that is pumped down into the well under high pressure. In order to allow it into the rock, a section of pipe is installed in the horizontal parts that has holes in it. These holes allow the fluid to penetrate the rock, and the pressure then widens the cracks. Repeating the process several times makes these cracks bigger and longer, and so a more significant volume of the rock can be penetrated, and pathways for the gas to escape back into the pipe are being created. This allows to extract most of the gas from the rock volume around the pipe section. Here you see a photo of a typical fracking site. Since the process uses large quantities of water and chemicals, most of what you see here are actually tanker trucks that bring in these fluids. So there's also a lot of traffic to and from these sites during the fracking process. Sometimes this can be reduced if there's access to surface water in the vicinity, so they take water out of rivers or out of lakes. Fracking fluid is mostly composed of water and sand, 98%, but there are also 2% chemicals in it. And these chemicals are currently not regulated, so they're typically trade secrets by the companies that do the fracking. However, the EPA is currently drafting rules that may require disclosure in the future. There's some knowledge about the chemicals that are being used. Since in New York State, material safety data sheets have to be filed if quantities exceeding 4.5 tons are used. There is some knowledge about typical chemicals that are in the fracking fluid. There was a study by Wood et al. Where they analyzed these data sheets, and they identified 17 substances that are classified as being toxic. 38 are classified as being acute toxins to humans, 8 are classified as known carcinogens, 6 are classified as suspected carcinogens, 7 are classified as mutagenic, and 5 are classified as having reproductive effects. And this list goes on, so if you are interested in this research, then please obtain this reference. Here we see an aerial photo of a typical well site. There are two wells and they are connected to a waste pit. This waste pit is typically just a depression in the ground that is lined with plastic foil. It is estimated that in one well up to 29,000 cubic meter waters and 580 cubic meters or 580 tons of chemicals are being used. About 15 to 80% of the fluid returns during flowback, and that's what's going into this waste pit. Conversely, of course, the rest stays on the ground and it enters the environment. It's interesting to note that the flowback also contains radioactive elements from the shale as well as heavy metals, but of course that is the same with most mining operations. It should be pointed out that some operations reuse the fracking fluid that comes back during flowback, and so the amount of discarded fluid is reduced. Other issues during the fracking process is the duration. It takes about 500 to 1500 days to frack, and during this period there's heavy truck traffic because all these fluids need to be brought to the fracking site. Interesting is also to note that wells often need refracking because once the gas is out of the cracks that were made with one fracking process, the well goes dead and the fracking needs to be repeated to widen the cracks in order to access more of the gas. Another issue is methane entering the water table. The process that is suspected at work is that because the fracked regions, the fracked volumes are below the water table, either gas escapes from the borehole that is used to access this volume, or that gas directly from fracked cracks that extend into the groundwater volume, that gas directly goes into the groundwater via these cracks, or that these cracks connect to previously inert cracks that then let the gas get into the groundwater. There is now scientific evidence that this is really happening. A recent study by R.B. Jackson et al. Measured methane, ethane, and propane concentration in private water wells in dependence on the distance between these water wells and fracked gas wells in the vicinity. And so you see here two graphs. The top graph shows the methane concentration in milligrams per liter that they measured, and on the x-axis we have the distance to the nearest gas well. And so you see clear that in a radius of about 3, 4, 5 miles there is a significant contamination of the drinking water wells with methane. And as we go further away, there is much less methane in the drinking water wells. Down here we see ethane concentration and propane concentration, and you see there's also a clear dependence between distance and concentration. This study clearly shows that there is a good probability that fracking really causes pollution of water aquifers. Yet another environmental concern is the greenhouse gas footprint of methane itself. We learned earlier that replacing coal with methane for power generation leads to a much lower carbon dioxide output. It's almost a factor 2 lower per energy output. However, methane itself is a much stronger greenhouse gas per molecule than carbon dioxide, and since methane is a gas, it can escape into the environment much more easily than, for example, oil. Methane leaks are concerned during extraction as well as transport, especially during the fracking process because of the high probability that gas is escaping through alternative routes. Methane is being emitted into the atmosphere. The good news is that methane has a shorter half-life in the atmosphere than carbon dioxide. This is a result of the fact that methane is a fuel while carbon dioxide is the end product of the reaction. So methane has a high likelihood to react with oxygen, especially under the influence of sunlight while it is in the atmosphere, and so it is finally converted into carbon dioxide. So if one wants to compare between the carbon dioxide and the methane impact on global warming, one needs to include a time horizon that takes into account when the methane was introduced in the atmosphere. In a recent study by Howard et al., it was investigated how the methane emitted from shale gas wells may influence the greenhouse effect in comparison to conventional gas, coal, and diesel oil. And so on these two graphs, you see the amount of carbon dioxide equivalent greenhouse gas that's being produced per energy from burning the 4 different types of energy sources. And so here we have shale gas, conventional gas, coal, and diesel oil. The color of the bars means the blue bars are the carbon dioxide that is directly emitted during burning the fuel. And so you see, of course, that gas, conventional and shale gas, is exactly the same here, and it is much better than coal and diesel oil. Now the orange bars, that is the carbon dioxide released during production and transport, and you see that all these energy sources are pretty similar in that. Now if we look at the pink bars, this is the methane that is being released from leaks, and so you see that shale gas, and this is low estimate, high estimate, so we have always two bars here, that shale gas has much higher estimates than conventional gas. And so they say that 3.6 to 7.9 of the total production of a shale gas well is actually lost to the atmosphere just through leaks. In fact, a large amount of this escapes during the fracking process when the fracking fluid comes back out. I think this is pretty obvious because once the rock is cracked and the gas is liberated, it will not stay down there and it's under pressure, and so it will come out with the fluid. And so what's coming out of the fracked wells is about 30 to 50 times more than what escapes from conventional wells. So we have considerably lower methane emissions from conventional wells. Now if you look at coal or diesel oil, there is much less methane that is escaping during the process. Whenever you mine coal, there is methane coming along, and when you extract fluids from the ground, there's always a certain amount of methane along with it. So this top graph is the 20-year time horizon. So this is the greenhouse gas impact over 20 years. And since methane degrades over time much more quickly than carbon dioxide, methane is of course more significant in the near term than when you wait, if you would wait 100 years and then the methane would have had time to degrade to carbon dioxide. So on a 100-year time horizon, this is shown down here. There we take into account that most of the methane has been degraded to carbon dioxide when the 100 years are over. And so the average greenhouse gas impact of all these fuel sources is actually pretty similar then. Now one could argue that in our situation with the global warming becoming stronger and stronger, the near-term impact is of course more important. But this here unfortunately also tells us that even on a 100-year time horizon, when the methane has equilibrated into carbon dioxide, gas doesn't have really an advantage over coal or liquids. So if this is true, the whole conversion from coal-fired power plants to gas-fired power plants may not make that much sense. This concludes part 1 of the unconventional fuel section. Thanks for watching.